We have seen tutorials where the user sends a prompt and some response comes out. But sometimes users ask for weird things and you need conditional logic, routing, retries, and memory. And LangGraph gives us a way to map that logic explicitly. So here's an example. We have an entry point from where the prompt comes in, an LLM node that decides what to do with it. Then it can send the state to either node after it. We also have another decision node that is called after API call that either gives it back to the prompt or send it to the end, after which a response is sent to the user. Another example where we can use feedback from another LLM. So few things to note here. Any of these nodes can be a LLM and even a LLM with tools attached separately. So all of these nodes can be tools as well, but inside a node there can be LLM with its own set of tools. For like it can be a special LLM that can perform a specialized set of tasks, and we can do things more deterministically in a more explainable way using this kind of a graph. Here's what we are going to build today. It's a simple ticket routing system where user sends a query and we extract that intent and then route it to one of the nodes where further actions are taken, and then at the end we send the response to the user. So this is our shared state. It's like the memory of our graph, and every node can see and modify this, and you have to define it once. This makes the whole system more predictable. This is just a JSON or a dictionary that we make once. All the nodes share the same state and modify it at every step. So there's state that traverses through all the nodes. In our example, first we get some raw text from the user. Our preprocessed node cleans the text, that is, just remove extra spaces from the input. Then we decide what to do with the text. Let's say we decide to send it to the billing agent, and after billing node is executed, response is sent to the user. A node is a plain function. You can pre-process text, query a database, do some maths, or even invoke an LLM. And what matters is it returns a dictionary. And the updates that it returns merges with the state. So for example, if there's a few keys and let's say key 1, key 2, key 3, and we return key 1 and value, only key 1 will be updated and others would remain the same. And the control flow in LangGraph is very deterministic and explicit. So we have to draw out the rules. So we have two types of edges. One is conditional and another is a normal edge. Conditional edge would extract some intent like billing from the state and send and select the next node to which it has to be sent. So here's how we would implement this. And we can have LLMs inside a node. So we have a system message where we ask it to classify. We also have a human message that we extract from the state, and then we pass it to our LLM. And in our case, it would be Gemini. So we give it the system message and human message, and it returns the intent using which we modify the intent in the state. So routing is what makes it actually intelligent. This function decides where the graph should go next based on the state. So one thing to notice here is it doesn't call the node, it just returns a node's label, which tells the LangGraph which node should be executed next. There's another way using which we can directly call another node. The advantages of using a LangGraph: we have explicit flow between the nodes, which is very critical for high stake operations. Multipath graph with parallelization, which means we can have parallel execution. So state would be passed concurrently to multiple paths. We can have short-term memory, which is per session, and long-term memory, which is across session. And we have a shared state graph that can be monitored at every step. And this is very transparent because we can print logs and make diagrams. Before we can start writing code, we would need access to API secrets. So we would go to Google AI Studio. We would create an API key. So if you do not already have created a project, click on create project and name it something. I would name it second app because I already have one created. So it'll take some time to create the project and then we can name our API key anything. I would name it key2 and then create key. So now we have an API key that we can copy to our env file. Then come to your project and create an env file at the same level as your notebook in which you are going to write the code, and create a Google API key secret and paste your secret here with or without quotes. That doesn't matter. So your secret here. I will paste mine and continue with the code. So first let's install what we need. We need LangGraph for graph logic. We need Gemini connector, which is LangChain Google GenAI. Typing extension for strong typings, and .env for loading our secrets from the env file. So it will take some time to install. Now let's bring in our imports. So system message and human message. Let us talk to Gemini with roles for system and human. Load env for loading environment. Typedict and literal give us a clean type for our state and router. These are LangGraph primitives. Now I load my Gemini API key from the environment and we check if it is there by loading it from our os.environment.get Google API key. And if it exists, we print successfully loaded Google API key. And this means we have it successfully loaded. Now we create a Gemini chat model. We give a model name. We'll be using Gemini 2.5 Flash. We provide the Google API key and set temperature to 0. That means the output will be very deterministic and it won't change much. So let's do a quick sanity check. So we get some message from Gemini. So that means it's working. Now let us define the state for our graph, which will be passed around to all the nodes. Text is the user's message. Intent is what the classifier will set. Reply is our generated answer from LLM, and nodes is just some extra debug info that we may use. Now let us create our first node, which is the pre-process node. Remember that every node in LangGraph is just a function that takes the state and returns an updated piece of it. So this first node trims the text, which is remove the white spaces that are extra at the ends of the string. It's like a basic cleaning process, and it just returns the text again, which gets updated in the state. So now let's add our first node, which is classify with LLM. This does the job of classifying the intent based on the user message. So first we create a system message telling it to exactly return one word. of billing, technical or other, based on the user's message. Then we create a human message from the text that is given in the state. And then we call the LLM with system message and human message. We again clean the text. If bill is in the message, we extract billing because LLM can return a sentence and we don't want to take any chances. If words like these are there, we classify it to technical, and this is the expected output. If the output is in one of these, we just return it directly, or else we return the default other, and then we return the state. Using a similar idea, we create the billing node. So if the intent is billing, we call this node. System message says it acknowledges the request, asks for some details, and we create a response similarly. So we have a system message, human message from the state, and then we invoke the LLM and generate the response and put that in the state. Similarly, we do it for technical reply and the other reply. Then we make our conditional edge, which is route by intent. So we get the intent from the state, or if it's not set, we use other as default. And if intent is billing, we return billing node. And if its intent is technical, we return the technical node, which helps LangGraph in deciding which node to execute next. Now let's wire everything together by creating a state graph and passing in the state. Then add all of our nodes, connect all of our nodes by adding all the edges, and then we compile the graph to see if there is any errors in the code. So for adding a node, we give its name and the function associated with it. So LLM can be used to call it. And for edges, we first give the source and then the destination for all of them. And then we have a conditional edge. So after the classify node, which calls the classify with LLM, we call the route by intent edge, which decides what the next node is going to be. And we can visualize our graph using display and image. So this is a mermaid diagram. So we can see at the start, we have a preprocess node. After that, we classify, and then any of the nodes could be called. So let's take an example of a billing issue. So from this, the LLM should be able to extract the billing. So we can see the processes that happened. So first pre-process was called, then classify was called, and then a billing reply was generated. We can also check for technical. Yeah, and that's it. We just built a full decision graph that uses Gemini for reasoning and handles branching automatically and stays completely transparent in the process. And we can also do more things with this. We can add memory, feedback loops, or human review nodes. So yeah, in the next videos, we would be adding persistent memory. So graph can remember context between runs.